Okay, so right, so let's do a quick recap on what we did in the morning before this whole problem happened. Well, we started by talking about languages. We took C programming language as an example and said that it has an alphabet. And then we said the alphabet is finite and non-empty. And then we said that using the symbols in the alphabet, we can create programs, which in automata theory we call strings. And then we discussed what a valid program in C could be. Okay, and then we defined a set of valid programs, P1, P2, and so on. And then we said that if you want to check a given program Pn, if you want to check the validity of this particular program, what do? Which we compare it against this entire set of valid programs in C. Okay, so then we generalized it to say when we are given a particular language and a particular string, how do we check if the string is there in the language or not? In other words, whether the string is accepted by the language or not. Okay, so we took an example like this, and then we discussed if string S1, which was AA, is present in the language. It was present. And then we discussed if S2, which was AAA, was present or not. To check this, what did we do? We compared this string against the strings in the language. Okay, so we said that is possible because that particular language is finite. We had only 4 strings in that language, so it was finite, and it was, I mean, we were able to do the comparison. Okay, but the problem arises when the language is infinite. So in those cases, we have to come up with a finite representation of the language to check the um, availability or the acceptability of a particular string in a particular language. So we said that we need to have a finite representation so that given a language and given a string, we can say that the string is accepted by the language or the finite automata or rejected by the finite automata or the language. So we took an example where language L was the set of all strings that start with A. Okay, so this is infinite. Sigma was AB here. Then I drew this diagram. We did not discuss what this diagram was. I just drew this and said that this is a finite representation of this particular language which we have here. Yeah. Then I said that this arrow indicates the initial state, double circles indicate the final state, capital letters indicate states, while the simple letters are the alphabet or the terminal symbols. Okay, so then we took an example S1, string S1, AAB, and we checked if it is accepted or present in the language or not using the finite representation or the finite automata. Yeah, so when we take AAB, whatever said and done, we start with the initial state, which is state A. Then upon taking the terminal symbol A, input alphabet symbol A, we come to state B. මෙතන ඉඳලා ඒව දුන්නාම අපි යන්නේ B ටනේ. So we come to B. ඊට පස්සේ B ගේ ඉන්නකොට ඒව හම්බුනොතින් while we are at B, මෙතන ඉන්නකොට if we get A, what will happen is I come back to B. Okay, so again I'm at B. Then I have simple B. So while I'm at B, what happens if I get simple B as the input alphabet symbol? Again, I come back to itself. So I am at B. So A is my initial state. B is my final state. So upon scanning the entire string, what happened to me? I went from the initial state to the final state. Therefore, I say that the string AAB is accepted by this language or the finite automata. Okay. However, if I take an example such as, let's say BBA string B, I want to check if this is accepted or not. Okay, so I start with A, that doesn't change because that's the initial state. A will innakota, if I get a B, what happens is I go to state C. Okay, then at state C, if I get simple B, එතනමයි කරකෙන්නේ. එතකොට මං එතනමයි ඉන්නේ. ඊට පස්සේ එතන ඉන්නකොට ඒව හම්බුනොතින් ආයි එතනමයි තියෙන්නේ. මෙතනටම නෙන්නේ ආයි කරකෙල එක නිසා still I am at C. So I started at the initial state, that is fine, but this is not my final state. Therefore, this string does not take me from the initial to the final state. Because of that, I say that this string is not accepted by this finite automata or the language. Okay, so we say that a string is accepted by a language if upon scanning the entire string, I can go from the initial state to the final state of the finite automata. Okay, right. Now we are going to classify these finite automatas or finite representations. හරි මෙන්න මේ જાති කට්ටියව classify කරන්නයි යන්නේ. Finite state machines ඕන එකක් කියන්න පුළුවන්. So finite automata has two main classifications. We say we have finite automatas which generate an output, and there could be automatas which do not generate an output. Okay, so the ones who generate an output are called transducers, and the ones who do not generate an output are called acceptors. Okay, now this has another classification. We have Moore machines and we have Mealy machines. And then this one has two classifications. I have DFA and NFA. These two are the ones which we talk in particular. So DFA කියලා කියන්නේ deterministic finite automata. NFA means non-deterministic finite automata. Okay, so we'll be talking about all of these during the lecture series. Today we're talking about this one in particular, DFA. Okay, deterministic finite automata. So this is a finite representation, just like we discussed before. However, this is going to be deterministic. Let's see what that means. Okay, now when we talk about DFAs, there's a way that we represent or define a DFA. Okay, it's like the tag which we stick to it. So a DFA is defined by a 5-tuple. Do you remember last week we discussed under tuples, 2-tuple, 3-tuple, so this has 5 parameters. Okay, this Q is the set of states. Okay, set of states කියලා කියන්නේ මොකද්ද? දැන් මේක ගත්තොත් capital A, B, C. That is the set of states in that. Okay, then sigma කියලා කියන්නේ input alphabet එක. So in the previous case, that is simple A and simple B. Okay, then we have delta. Delta is a function. Okay, delta is a function between Q cross sigma to sigma. This we call the transition function. Let's talk about that transition function. Okay, this Q cross sigma කියලා කියන්නේ Cartesian product එක. ගේ සතිය අපි කළා මේක. And then we have Q naught. This is the initial state. එතකොට කලින් example එකේ initial state එක capital N. එතකොට ඒක තමයි එතෙන්ට එන්නේ. And remember this Q naught is දැන් මෙතන states වලට තියෙන ABC නම් මෙතන initial state එක A නම් A is going to be an element of Q. Yeah. So because of that, Q naught is always an element of Q. And finally we have F. F කියලා කියන්නේ final state එක. We cannot say that there's only one final state in an DFA. Because of that, we say this is a set of final states, okay? Which means we can't say that only to make C also a final state, okay? Therefore, these representations can have more than one final states. Because of that, we say that F is a subset of Q. It's not an element, it's a subset. Q kina set එකෙන් ඕනම කැලලක් final state එක වෙන්න පුළුවන්. Okay, so this is the way that we define a DFA. Wherever we draw a DFA, wherever we come up with a DFA, we have to define these people on that particular finite representation or finite automata. Okay, now we discussed about, now we know what Q, sigma, Q naught and F are. This delta, මේ delta කියන්නේ මොකක්ද කියලා බලමු අපි. So we said that delta is a function between Q cross sigma to Q. හරිද? එතකොට දැන් අපි කලින් කරපු මෙන්න මේ example එක විතර ගත්තාම Q ලට එන්නේ මොනවාද? ABC. Sigma to මොනවාද එන්නේ? Simple A simple B. I අනිත් පැත්තේ Q ට එන්නේ ABC. Okay, so this is how the function basically works. So if you remember last week we did this Cartesian product. එතන මේ දෙන්න Cartesian product එකට මොනවාද අපිට මේවා එන්නේ? මොනවාද මේ උත්තරය එන්නේ මොනවාද? We will have pairs. A එක pair එකක් වෙනවා. AB BA BB CA CB. Okay, so this is what we have for Q. Sorry, Q cross sigma. A දෙකට මෙන්න උත්තරේ ඕක. Okay, then on this side we have what? A, B and C. හරි. දැන් අපි බලමු මෙන්න මේක බලන්න. Okay, see, now if we are at A, okay, and we are given the input symbol A වල ඉන්නකොට capital A state එකේ ඉන්නකොට simple A input එක ආවා මම කොහෙටද යන්නේ? මම යන්නේ B වලට. Which means when I'm at A and when I get the simple A input symbol, where do I go? I go to state B. Okay, I'll draw that here. නැත්තම් උඩට යන්න වෙනවා හැම වෙලේම. This is the same thing which we drew earlier. Okay, then the next one. When I'm at A and when I get input symbol B, where do I go? I go to state C. Then when I'm at B, capital B, and I get input symbol A, මම එන්නේ එතෙන්ටමයි. කරකිලා එන්නේ එතෙන්ටමයි. B දුන්නහමත් එතෙන්ටම තමයි එන්නේ. Finally at C ට input symbol A දුන්නත් B දුන්නත් I come back to C itself. So එතනත්මයි යන්නේ C. Okay, this is delta. This is how the function works. Q cross sigma to Q. Okay, now there's something important which we need to see here. Then do you see that every state A කියන state එක ගත්තාම we have outgoing edges on input symbol A and input symbol B. හරි, ඊට පස්සේ input මේ මොනවාද capital B state එක ගත්තාම edge එකේ ඉන්නවා symbols දෙකම. C ගත්තාමත් symbols දෙකම ඉන්නවා. So in a DFA we need to have a transition defined on every input symbol for every state. There cannot be any state which doesn't have a transition defined on a particular input symbol. Okay, which means කවදාවත් DF එකක් තියෙන්න බෑ. මෙන්න මෙහෙම විතරක් තියෙන input symbols A B දෙකම ඉන්නවා නම්. දැන් මේකේ අපේ sigma හිටි A B නේ. We have to define another transition for B as well. එක්කෝ එහෙම එක්කෝ A B දෙකම මෙතන තියෙන්න ඕනේ. මොකක් හරි විදිහකට both input symbols should be defined on each state. Okay, and the next important thing is a DFA will never include something like this. It is an input symbol A එකටම යනවා C වලට. These type of transitions are not allowed in a DFA, which means the same input symbol cannot take you from one state to multiple states. One input symbol will only take you from one state to another state. Okay, so these are not allowed. This is what is allowed. And then the other thing is that this is also not allowed because a transition on simple B is not defined. Okay, so each state has a transition for each input symbol, for each symbol. And that transition is exactly one. There's only one, exactly one transition defined on each state for each input symbol. Exactly one කියලා කියන්නේ at most one and at least one. එකම තමයි. ආයෙක වෙනස් වෙන්නේ නැහැ. That is why, because we say exactly one, that is how the word deterministic comes to finite automata. Deterministic කියන කෑල්ලෙන්නේ ඔන්න ඔතනින්. F කියන එක අපි කොහොමද දන්නවනේ? It's a finite representation. This is how D comes in front of that thing. Okay, right. So that is how delta works, and this is the introduction to DFAs. Okay, right. Now let's see an example. Okay, now let's say we want to construct a DFA. We want to construct a DFA that will accept strings of length 2. Our sigma will be AB as usual. And this DFA will accept the language where you have strings of length 2. Length 2, okay? Which means, then I make a language එක ලියුවොත් අපිට මොනවද එන්නේ? අපිට එදා ඉඳන් කතා කරපු එක AAAB. This is going to be my language. Okay. Now what do I need to do? I need to construct a DFA. Okay. So whenever you are asked to construct a DFA, the easiest thing to do first is to come up with the basic diagram for this. Basic diagram basic skeleton. The automata which will accept the smallest string in the set of strings. Okay, string set එකේ පොඩි මෙක්කනාව accept කරන basic skeleton එක අඳගත්තට පස්සේ you can expand it further ඉතුරු වලට ගැලපෙන විදියට. Okay, so let's first draw the DFA which will accept AA. On now I will have an initial state that is a master. එතන ඉඳන් පටන් ගන්න. Yeah, so I need to accept AA නේ. So upon giving A, I should come to a state. Then I have the next A, then I should come to a state. And now since this string is there in the language and that should be accepted by the language, C should be a final state. Not accept කරන්න බෑනේ අපි ගෝනේ final එකට යන්නත් accept වෙන්නේ නැහැයි කියලා. So C has to be a final state for that. Okay. Then we check whether this is a DFA already. දැන් මේක DFA එකක්ද? නෑ. ඇයි? We haven't defined the transition for these states on simple B input. අපිට එකකින් නවත්තලා ඉන්න බෑ because DFA say that they want transitions defined on each input symbol. Okay, right? So because of that, now we are going to see what will happen to B. Then බලන්න පළවෙනියට එන අකුර එක්ක A වෙන්න පුළුවන් එක්ක B වෙන්න පුළුවන්. So I need to have B also here. නැත්තම් B ගන්න විදියක් නැහැ. Then දෙවෙනියට එන එක also can be A or B. Okay, second one also can be A or B. So I put that as well. Got it? Okay. Now this string, not the string, this what do you call automata will accept these four. But the thing is, now is this a DFA? No, it's not. Still no. Why? මේ දෙන්නට නම් හරි. අපි A B දෙකම කියලා තියෙනවා, but for C we haven't told what will happen if C gets A or B. හරි, C final කියලා නිකන් ඉන්න බෑ. C ටත් අපි කියන්න ඕනේ what will happen if C gets an A or a B. Okay. Now let's see what will happen if C gets an A or a B. Now say now our DFA accepts strings of length 2. Okay, so if we write here the length of the strings that I get at state A, my string length will be 0. State B, my string length will be 1. At state C, my string length will be 2. After C, any input symbol which gets added to the input string will exceed this constraint that I have given initially for length. Yeah, which means මෙතනින් එහාට එන ඔක්කොම යන්නේ greater than 2 කෙනකට. Greater than 2 ලව මම මේ language එක accept කරන්නේ නැහැ, because I have clearly said that strings should be of length 2, which means more than 2 are not accepted. Because of that, what do I do? C ට පස්සේ කවුරු ආවත්, C ට පස්සේ A ආවත් B ආවත්, I don't care. What do? I have to send them to a state, okay, which is not a final state, which is a normal state. අයියා final කරන්නේ නැත්තේ because මෙතනින් එහාට යන කට්ටියව C ගෙන් එහාට යන කට්ටියව I don't accept මොකද length එක වැඩි හන්දා. So it is a normal state and there's no coming back. මෙතනින් මෙහෙට එකක් හරි B එකක් හරි ඇවිල්ලා ගිය ගමන් there's no coming back, which means those strings will be rejected. Okay, so that and anybody, then උදාහරණකට අපි හිතමුකෝ ආවයි කියලා A කියලා එකක්. Okay, so A I'm initially at A, capital A, I go to B, මෙතනින් ආවම I go to C, and now I go to D. Okay, so D is not the final state, so this is rejected. දැන් හිතන්නකෝ A B ඔහොම එකක් ආවා කියලා, then what will happen? I go to B, I go to C, I go to D. මෙතනින් එහාට I don't have a state that I've defined. Yeah. එහෙනම් මම මොකද ගන්නෙ? මම මෙතන ඉතලයක් ගාලා ආයි state එකක් දාන්න ඕනේද? නෑ, because if I do that ඔහොම දිගටම යන්න වෙනවා. දැන් මෙතනින් එහාට කාවත් ගන්න නැති නිසා මොකද මම කරන්නේ? මම මෙතනම දානවා. ඔතනින් එහාට after that particular place, anybody who comes after that are rejected. Okay, so මෙතනට B ආවොතින් again I'm at D, rejected. I එකක් ආවොත් again I'm at D, rejected. So these will be rejected. Got it? So this is the DFA, which will accept strings of length 2 that are defined over sigma AB. Got it? Okay. Now there's an important point which I want to highlight here. Now you saw that the string length here is 2. මෙතනට D ආවම 3යි. මෙන්න මෙතන මේ AB කියන එක්කෙනාව recurse කරලා තියෙන 3 or more. Okay, 3 or more, everybody is rejected. Okay, so now this particular state D, if somebody goes to D, there's no coming back of D. You saw here when these people got to D, there's no coming back. ඔතනින් එහාට I D ම තමයි repeat වෙන්නේ. So that because of that, we call this state a trap state. A trap state or a dead state. Okay. We use this term in finite automata because there's no coming back to the final state when you go to a trap state. So usually you use a trap state. In FAs, when you want to define or when you want to show a particular part in the automata which should be rejected, which will reject the strings. එහෙම වුණාම අපි trap එකක් දාලා ඒ කට්ටිය වෙතෙන්ට දානවා. ආයි පස්සට එන්නේ නැහැ. Okay? Right. So now you understood that up until this point, when the මෙතෙන්ට එනකම් C වලට එනකම් until C, when the මෙතෙන්ට එනකම් my automata accepted everyone who was in the language. මේ හතර accept කළානේ automata එකෙන්. So this part defines the strings that are accepted by the language. Yeah. එතර අපි මේ කැලල මොකටද යන්නේ? මේ කැලල අපි යන්නේ to show, to depict the strings that are rejected by the language. Rejected, strings that are rejected. Okay. So when we take them as a whole, the entire automata depicts the strings that are accepted and the strings that are rejected, which means we cannot stop our finite automata, RDFA, at the point where we understand that the strings which should be accepted are being accepted. We have to go a step further and draw the part which will depict the ones who are being rejected as well. හරිද? ඔය දෙකම එකට ගත්තාම තමයි අපි හරි finite automata එකක් අඳින්නේ. එතකොට තමයි අපිට හරියට කියන්න පුළුවන් මේ language එක මේ finite automata එකෙන් represent වෙනවා කියලා. තේරුණාද? So with that, we come into two things. One is called string acceptance. And the other one is called language acceptance. හරිද? String acceptance අපි දන්නවා. මොකද string acceptance කියන්නේ? A string is accepted by a finite automata if upon scanning the entire string you can go from your initial state to the final state. If that is so, we say the string is accepted. If that is not so, we say the string is rejected. Okay. Language acceptance කියලා කියන්නේ අපි දැන් මේ කතා කරපු එක කලින්. මොකද? We say that a language is accepted or language is represented by the finite automata if the strings that are in the language are accepted, okay, and the strings that are not in the language are rejected. We say that this particular finite automata represents the language. Did you get it? If a finite automata accepts your language, then it will say that the strings that are in the language are accepted and the strings that are not in the language are rejected. Or we say the FA represents the language. Okay, if that is so, the language is accepted by the finite automata. Okay, then make let's say let's take a small the simplest automata, simplest DFA on then here you have only one state, and that state is the initial and the final. That state is the initial state and the final state both. And we have shown how the transition happens as well. Upon getting simple A and simple B, state A will be at state A itself. Then this automata will accept anything. Okay, this accepts epsilon. Null string එක පවා ගන්නවා ඇයි first state එකම final වෙලානේ. එතකොට මුකුත්ම නැති වුණත් null වුණත් acceptance එනවා. Because the initial state is the final state. Length 0. මෙතන අපි කිව්වේ length 0 strings කවුද? Null strings. මෙතෙන්ට එන්න කවුද? A O B. මෙතෙන්ට එන්නේ A A B ඔය කට්ටිය. Okay, so null string is accepted by this. Then A ආවම ගන්නවා, B ආවම ගන්නවා, A ගන්නවා, AB ඔය set එක ගන්නවා. ඊට පස්සේ 3ක් ආවොත් ඒකත් ගන්නවා. 4ක් ආවොත් ඒකත් ගන්නවා. So everybody is accepted by this particular finite automata. Okay, because of that we can say that this is an FA for this language as well. මෙන්න මේකට මෙච්චර දඟලන්නේ නැතුව without drawing this entire thing අපිට මෙන්න මේක ඇඳලා දාලා කියන්න තිබ්බා that this is the finite automata that which represents that particular language. Okay, because මේ මෙන්න මේ set එක accept කරනවානේ. ඔය ටික තමයි අර language එකේ තිබුණේ. But it is not so. Why? Accept කරන කට්ටියව මෙයා ගන්නවා. හරි. ඒ කැලල හරි. But the ones who are not in the language are not rejected by this finite automata. Okay, මෙන්න මේගොල්ලන්වත් මෙයා accept කරනවා. නමුත් ඒගොල්ලෝ language එකේ නෑ. Because of that, the ones who are not in the language are not rejected by the finite automata. Because of that, this is not the FA for that particular language. Okay, so to say that a language is represented or a language is accepted by a finite automata, you have to show the ones who are accepted, the strings that are accepted, and also you have to show the rejectance of strings as well. Okay, I hope that part is clear. All right. Now let's do an example. Okay, let's construct a DFA which accepts strings. I mean a DFA which accepts strings of length greater than or equal to 2 over the alphabet AB. හරි. එතකොට මොකද්ද? දැන් W කියන්නේ string එකක් නම් if W is a string in this language, length of W modulus W will be greater than or equal to 2. Okay, so we start initially with state A. Hari. Before that, let's define the language here. මොකද්ද මේ කතා කරන language එක මේගොල්ලෝ? Greater than or equal to 2. Okay, so I can have strings අර කලින් set එක එනවා. ඊට අමතරව I can have anybody else. A ඉඳලා up to B. Then A indala up to everything. Okay, after that anybody is accepted by this particular finite representation. Okay, so let's draw the skeleton first. For AA, that is the same thing as before. AA should be accepted, so we do the double circle there. Then B also should be here. B තෝන ඉස්සරහට B තින්න පුළුවන් සමහරලාට. And after that, now what are the lengths here? Length of the string that is coming to A is 0, coming to B 1, metenta 2. So strings of length 2 are accepted here. Then we have this equals mark as well. That means anybody who is greater than 2 are also accepted. Because of that, I say anybody who comes after that 2 or more, and ඔය ටිකට I say it should come back to C. Okay, you can හිතන්න තිබුණා කියලා A B කියලා. This is the string. If that is so, when I get A, I go to B, then I go to C. I'm at C, I come back to C. This is the initial state, this is the final state. I go from initial to final, accepted. Okay, right. So this diagram, this automata will accept the strings which are of length greater than or equal to 2 එකනේ at least දෙකක් at least 2. Okay, right, I hope that example is clear. Then අපි ඕකම ටිකක් වෙනස් කරමු. අපි කියමු that I want a DFA which will accept strings of length less than or equal to 2, which means at most. Meaning length of the string should be less than or equal to 2. So what are the lengths I'm going to accept then? I will accept 0 lengths, strings of length 0, strings of length 1 and 2. That's all. I don't want anybody who is more than 2. Okay. Which means the language will be 0 in කවුද epsilon, එකෙන් ඉන්නේ කවුද a and දෙකෙන් ඉන්නේ අර set එක BA BB. Okay, right, so I start at A. Upon getting A or B, I can go to B. Upon getting A or B, I can go to C. මේ කලින් ඇඳ පිටිකමනේ. Okay, now there's a thing here. Now since I want epsilon to be accepted, what should I do? I should make my initial state a final state. Okay, then I want A and B to be accepted. A and B කියන දෙන්න. A තනියම B තනියම ආවත් they should be accepted. Which means then අපි strings වල lengths ගත්තොත් මෙතන these are 0 length strings, 1 length, 2. Yeah. එතන මේගොල්ලන්ගේ length එක 1යි. They should be accepted. Therefore this should be a final state as well. Yeah. C is anyway final. එතන මේගොල්ලන්ව accept උත් වෙනවා. Okay, now accepting ones are done. Accept වෙන කට්ටිය වන්දලා ඉවරයි. Okay. Now we have to look into the ones who are being rejected. Yeah. So anybody who is more than 2 should be rejected. එතකොට අපි අර කලින් කළා වගේ අපි අර trap එකක් දැම්මේ. මෙන්න මෙතන trap state එකක් දැම්මා වගේ දෙකෙන් පස්සේ එක්කෙනෙක්වත් ඕනේ නැති හන්දා what do? We say after C whoever comes A or B they are sent to a trap state. ඊට පස්සෙත් කවුරු හරි ආවොතින් anybody they'll be sent to the trap state. Okay, so this is length 3. Length 3 ones are rejected, and this recursion is to say or more. So 3 or more, anybody who's 3 or more are rejected. Okay, right, so this is the minimal deterministic finite automata that we can draw to depict this particular case. Okay.